This is 7.5.2. Charged particles moving perpendicular to B fields, which are magnetic fields. So first I'm going to draw a uniform magnetic field, which is into the paper. And then we can draw some electrons that are moving perpendicular to this field, so coming in from the bottom. So these are electrons moving upwards until they enter the field. Now, if electrons are moving, that means that their charge is moving with them. And a moving charge means that there is a flow of charge, which is a current. Now, electrons have a negative charge. So if they're moving upwards, that means negative charge is moving upwards. But conventional current is defined as the movement of positive charge. So if negative is moving upwards, upwards is becoming more negative, while below it becomes more positive. So the current is actually moving downwards. So current is always in the opposite direction to electrons, but will be in the same direction as the movement of a proton. So when we apply Fleming's left-hand rule, we're going to align our current as opposite to the motion of electrons. Yeah? So let's do this now. As that electron enters the field, we use Fleming's left-hand rule for FBI. B is into the paper, and we have to rotate our middle finger so that it points downwards, because current is opposite to the motion of electrons. So we can see that in the beginning, when it enters the field, these electrons experience a force to the right. So as they're moving upwards, they're going to accelerate to the right, so they're going to curve towards the right. So I'm using a dotted line. I'm going to start showing this curve. Now, I'm going to stop over there, and we're going to do the same thing again. At this point, as it gets to the top, which way are these electrons moving now? They're moving to the right. So let's just see Fleming's left-hand rule again. If I put it there, and this time I rotate to the right, so the current has to be moving to the left. It's in the opposite direction. Which way is the force now? It's down. So now these electrons are going to curve downwards until they reach there. At this point now, which way is the current?
Going down, so you make it go up.
So the electrons are going down, so the current has to be upwards. So when we do that, we feel a force towards the left. And so they curve towards the left until they reach this position. And then you can see that they basically go in a spiral or a circle. They experience circular motion. At any point where the electrons may exist, so I'll draw some positions where they will exist. It experiences a force to the right, so I've labeled that as FB. Over there it experiences a force down, FB, to the left and upwards. Yep. So at any point, the electrons experience a centripetal force, a force directed towards the center of that circle. I'll make a note here that current is the movement of positive charge, and we'll just underline the word positive. So current is opposite to electron motion.
negative charge of the electrons is moving upwards, technically there's no, like you could say where there are no electrons, it's more positive, but
It becomes more positive as the electron leaves that place.
technically it's not that positive charge as you would normally see.
No. It's more positive than when the electron existed there.
Okay.
So at that point, put your finger on it, is an electron at that point? What's the charge there? It's negative. As the electron left that point, what's the charge there? Nothing. Well, nothing is more positive than negative. So, force is always perpendicular. And you can do this again. So we can make an infinite number of points along that circle. And wherever you do it, so wherever you do it along here, you'll see that as you rotate your hand around that circle, your thumb, which represents the force, is always going to point towards the center. One second. So force is always perpendicular to the velocity of the electrons. Which gives circular motion. Put that in a box. And here we can say, use Fleming left-hand rule to verify. You got a question?
Yeah. When the electrons start moving in the circle, they just form a circle or they form an inward going spiral?
In this case, it will be more of a spiral because at some point, as they entered the field, right? So they're doing kind of circular motion, but at some point they'll end up leaving the field. They may leave the field. Let's assume they started in that field and we suddenly gave it some velocity in that field already, and the field is sufficiently large enough that it can't escape, then it will do circular motion. So if I magically just input an electron in that field, or if I have an electron moving vertically upwards and I turn on a field at that instant, so the field is like generated by an electromagnet. So it wasn't on and I turned it on, and the field was large enough that the electron can't escape the field, it will move in a circle. So forces on moving charge. I'm going to give you an equation for this now. So force on a moving charge. Now this is important. The charge has to be moving. If a charge is stationary, magnetic fields do not affect them. Magnetic fields only affect moving charges. So force on a moving charge is given by BQV. So F is force in newtons. B is magnetic flux density. Measured in Tesla. Q is the charge in coulombs, and V is velocity, measured in meters per second. Now, if the magnetic field is causing circular motion, then we've got BQV equals to mr omega squared, or BQV equals to mv squared over r. Put boxes around these. Let's do an example. So if we have a Large Hadron Collider, this is a very, very large circle. It's got a circumference of 27 kilometers, and it accelerates protons to 0.98 C. We're going to assume there are no relativistic effects. So relativity has no effect on these protons. So assuming no relativistic effects,
What's that?
how big is the B field? Now, mass of a proton is 1.67 times 10 to the minus 27 kilograms. And the speed of light is 3 times 10 to the 8 meters per second. So you can pause the video here to attempt the question and then play the video again when you're ready to see the answer. Right, to start this question, we need to figure out what the radius of the Large Hadron Collider is. So, we know that the circumference of a circle, and I'm going to use L to represent the circumference, so the length of the circumference of the circle, rather than C, because I don't want C to be confused with the speed of light. So, L, the circumference, the length of the circumference, is equal to 2 pi r. So we want to find the radius. So we rearrange this equation to get r equals to L over 2 pi. And L was 27 kilometers. So that's 27 times 10 to the 3 all over 2 pi. And we'll hold on to that for now. We won't need to actually calculate it. Then we equate the force experienced due to the magnetic field to the centripetal force. So BQV equals to mv squared over r. The question asks us to find the B field that allows this to happen. So we're going to rearrange this to get B. So B equals to, we'll move the Q and the V to the other side. That's mv all over QR. And now we can start substituting our values in. So m is 1.67 times 10 to the minus 27 times by the velocity, which is 0.98 times by the speed of light, which is 3 times 10 to the 8, all over the charge of the proton, which is 1.6 times 10 to the minus 19, times by the radius, which was 27 times 10 to the 3 over 2 pi. So 2 pi will go above. And times that all by 2 pi. So you put that into your calculator. That gives us a B field of about 7.14 times 10 to the minus 4 Tesla. Now notice that this is quite small, a small number. So in terms of magnetic fields, 1 Tesla is quite large, especially when we're talking about subatomic particles being accelerated. Right, start a new page. Now you need to learn about a type of a particle accelerator called a cyclotron. A cyclotron is essentially two metal semicircles hollowed out with magnetic field lines going down. So there's a B field here. These two are connected to a circuit, which is an alternating current. And these hollowed out semicircles are electrically charged. Because they're connected to an alternating current, each of these semicircles can change polarity. So there's a frequency at which they change. So AC allows for changing polarity. And these semicircles are called Ds. So an electron is fired perpendicular to the B field between the Ds, and it causes that to accelerate the electron. So we're going to look at what that looks like now from above. So from above, we've got the Ds, and we've got our magnetic field going into the paper. So if our electron started here, then what would happen is the electrons will go between the two Ds, and it will spiral as it accelerates until it leaves and moves towards a target. So what happens is, as the electron is moving in a spiral, we can simplify that to say that the electron moves in 4 directions. It moves towards the right, it moves down, it moves towards the left, it moves up, and that repeats. So if you essentially look at a circle and simplify that to, well, a circle kind of does the same thing as a square, right? But a square does it as sort of discrete directions, whereas a circle curves into each different direction, right? So it goes to the right, down, to the left, up. So think of it as a square for now. Those are the 4 directions. While the electron is moving up or down, it's not accelerating. It only accelerates when it moves between the two Ds. And the way that happens is if the electron is on the left side, so on the left D, at that moment, the current will flip so that the left D becomes negative and the right D becomes positive. So there's an electric field. So the electron is repelled by the negative D and is accelerated towards the positive D. Now as it reaches there, when it reaches that positive D, the alternating current switches, so there's a frequency of switching, it switches so that the right hand D now becomes negative, the left hand D becomes positive, and at that point the electron's curving around due to the magnetic field, and then is then accelerated and gets faster and goes towards the left D, and then again it flips and it repeats over and over again. Every time the electron's accelerating, its radius also increases, because BQV equals to mv squared over r. So if you rearrange it, you can see that as v increases, everything else remains constant, so the radius has to increase. And it will do that until eventually it leaves the Ds and also leaves the magnetic field as well. Yeah? So electrons accelerate as they move across the gap. So only in the horizontal directions. So we can say that mr omega squared equals to bqv. Now the frequency has to be related to omega, because as these electrons are essentially moving around in a circle or in a spiral, the frequency at which you flip the D's has to match with the angular frequency of these electrons. So if an electron does one full circle, within one full circle, one D will switch from positive to negative and back to positive again. So it will do one oscillation of switching. That's basically one oscillation of an alternating current. Now, so we start with this equation. Now we know that omega is equal to V over R. So V is equal to omega R. So we can make this substitution first. So we get rid of V and we put omega. So mr omega squared equals to bq omega R. If we now rearrange this, omega can cancel on the other side, and we can bring m and r to the other side. So if I did omega equals to bq over mr, but then the r's will cancel out, so it's bq over m. Then we know that omega is equal to 2 pi f is equal to bq over m. And we can move the 2 pi to the other side. So we've got bq over 2 pi m. Now this is an important equation to get to. So we said that the flipping frequency of the D's is related to the angular frequency of the electrons moving in a circle. And then we've got that the frequency is equal to bq over 2 pi m. Well, B is a constant. The magnetic flux density is a constant. We have a uniform magnetic field. The charge of the proton is constant. And the mass of the proton is constant because we're ignoring relativistic effects. So that shows us that the flipping frequency of the D's is constant. And in brackets, I'm going to put ignoring relativity. Now, that comes with some limitations. If we are ignoring relativity, that means that this equipment cannot be used when relativistic effects are relevant. Yeah.
You know, the flipping frequency is constant, but isn't the electron accelerating?
It is.
So wouldn't the flipping frequency have to like increase as well?
No.
Match the speed of the electron?
No. Because the electron moves faster, but its radius also increases. So its angular frequency is not changing. It's still doing one circle. Yeah, it's still completing 360 degrees of a rotation in the same amount of time. But instead, its radius is increasing, so it has to do a bigger distance with each circle. if we kept the size of the circle the same, so it was accelerating within a circle, then the frequency would have to change as well. But that's not what happens. It spirals outwards, keeping omega the same. So let's get some limitations. So 1, the cyclotron has to be large enough so that the particle you're accelerating can do orbits inside of it. The cyclotron can't be smaller than the orbits. So in other words, if you look at the diagram we drew above, when the electron gets to the point where it spirals out of the Ds, out of the cyclotron, you can't accelerate any further than that. So we're size limited. And then the flipping frequency will need to change. When you have relativistic effects. You get relativistic effects when you approach the speed of light. So if you're moving relatively slow compared to the speed of light, relativistic effects are negligible. They're so small they don't do anything. But when you get closer and closer to the speed of light, so if you're like 0.8 of the speed of light, 0.9 of the speed of light, very quickly relativistic effects become important. So we're limited to how fast we can accelerate these electrons or any particle too. So relativistic effects become non-negligible near the speed of light. And that basically means the mass of particles increases and when the mass increases, well now, according to that equation, if mass is now a variable, then F needs to be a variable. So that poses a problem. It's going to be quite difficult to synchronize that changes of frequency according to your particle that you're trying to accelerate. It's very easy to accelerate if you can keep everything constant and just fire the particle and let it go. But now when you consider relativity, then it becomes a bit more complicated. So at this point, if you need to synchronize these, rather than using a cyclotron, you'll now use a different kind of a particle accelerator called a synchrotron, which we'll look at in more detail when we get to turning points. So you would use a synchrotron instead. And that's near C. And that's the end of 7.5.2.